We are not learning any new derivative rules. We are done. We have learned every derivative rule that we need for this class. So we are done with that. What we're doing now is, what were those for? What is the derivative useful for? Why did we spend all that time learning it? How is it applicable to real life? What can we learn from derivatives? So this is going to be the application of everything from chapter 2 and chapter 3. So this is it. Like if you're thinking like word problems, yes, this is word problems. This is the writing, the most writing you've been able to do, explain and justify and show how you would know. Graham, would you mind taking that out for me? So what we're going to focus on today is the use of the derivative in something called first derivative analysis. Do you remember we did this technique with velocity? We made these little charts and we did pluses and minuses. Okay, we're going to use that a lot this semester, or this chapter, this particular unit, to help us kind of decode what the derivatives are good for. So that's going to be a key thing that we're going to be focusing on. But we're going to start with first is a theorem. We've done one theorem already, the intermediate value theorem. This is our second one, called the extreme value theorem. Anytime you use a theorem, you have to be working with a continuous function. That is key. If it's not continuous, the theorem doesn't apply. Okay, so there can be no asymptotes, there can be no breaks, gaps, jumps, anything that would make it discontinuous. It has to be continuous. The next thing that this particular theorem requires is brackets on that. Now, what do brackets mean? Inclusive. It includes it, which means we have to have endpoints. There can't be open circles. There has to be closed circles. So that's going to be, you have to have two closed circle endpoints. If you don't have that, then this theorem doesn't work either. So you might be asked, does the extreme value theorem apply? And you would have to say, yes or no, like yes, the requirements are met, or no, it doesn't meet one of these requirements. Now, differentiability is not required. That means corners are okay and cusps are okay, just not discontinuities or open circles. All right, what the extreme value theorem says is if those two things are true, so everything theorem will start with an if, and then it goes to a then. So what's the then? The then in this case is that you are guaranteed both a maximum and a minimum. Bless you. So that means any graph or any function you look at that meets the requirements is guaranteed to have a maximum and guaranteed to have a minimum. So let's just take a look at this one. What kind of graph does that look like to you? Okay, probably, could be cosine also, but it's a trig graph, right? It's sine or cosine. Is it continuous? Yes, it's continuous. All right, does it have endpoints? What's the first endpoint? A, and the second endpoint, B. You could infer that there are dots there. So that means that the extreme value theorem guarantees that there will be a max and there will be a min. Can you just look at it and tell me what the max is? Yeah, it's right here, right? Capital M for max. And you can find the minimum as well. It's a bummer. They use lowercase m for min. Why is that problematic? What else do we use lowercase m for? Slope. Yeah, it's unfortunate. All right, but uppercase typically means the max, lowercase would mean the min. Yep, so they're there. I can see them. All right, move on to the next one. This looks like a piece of, I don't know, what do you think it might be? The skateboard ramp, okay. What could have made that shape? Could be part of a parabola, sure. Could be part of an exponential graph. All right, but does it meet the requirements? Is it continuous? Does it have two endpoints? Yes, okay. And does it have then guaranteed a max or a min? So yes, the m is here, the max, and they lowered, they put the m in the funny spot, and a minimum is there. So yes, I can see that they are there. All right, how about this one? Continuous? Yes. Two endpoints? Yes. All right, a max? Yes, happening up here. So here's our max. Now a min. There are two, but one is lower than the other. So this one down here is called the absolute min. The other one, the other endpoint, is called a relative min. That means it's low, but it's not the lowest. So you could have two different kinds of mins, but we're guaranteed to have the absolute. That's what we're really looking for in this one. And then our last one looks like probably another piece of a parabola, possibly. Again, it's continuous. It has two endpoints, endpoint A and endpoint B. Endpoint B happens to be the absolute max. But we have another relative max. This one is relative. This one is absolute because it's the biggest of the biggest. And then you have your min down here at M. So the extreme value theorem guarantees that. Now, you might be thinking this is stupid, I can tell this, I can just look at it. The whole point of calculus is that I can ask you these questions and I can ask you to prove it to me without looking at the graph, and I won't give you the graph. I will give you a complex function that does not have a graph, and you'll have to use calculus to tell me where the maxes and mins are. Yeah?
Why is one relative max and one's relative min? Are they like interchangeable?
Yeah, so relative just means that that they are both low values. They're both lower than the maximum, but relative is just a modifier that means it's not as low as the other one. It's like relatively low. You could say it that way. It's relatively low, but it's not the absolute lowest.
What constitutes as a minimum instead of a maximum?
Well, look at the values before it. The values before it are all higher, so that way it has to be the lowest in that section. Whereas the other one over here, the values around it are all smaller than it, so it would be the maximum. You look at its y value. It has a higher y value than anything else nearby. Okay. All right. How do you tell then without the advantage of looking at a graph? Well, the thing that all of those maxes and mins have in common is they all have a horizontal tangent. And so we can find an extrema by taking our derivative and setting it equal to 0. This will find me all horizontal tangents. Now, a horizontal tangent could be a max or a min. You don't know the difference, but it could be a horizontal tangent. And then f prime does not exist will find you all corners and cusps. So if f prime equals 0 gives me a horizontal tangent, what should f prime be equal to give me corners and cusps? 1 over 0, right, anything undefined. So we've already practiced this. We've done, what else have we done that's 1 over 0? Vertical tangents, that's also undefined. So we'll be using the derivative set equal to 0, and we'll do some cross multiplying and some math, and we'll do the derivative set equal to 1 over 0, and we'll do cross multiplying and do some math. And that's going to find for us, without even knowing what the graph looked like, we know where all the horizontal tangents are and where all the corners and cusps are. So that is step 1. Step 1 is finding the local extrema. So for now, we'll just call them generic. Okay, there's going to be an extrema, a horizontal tangent at A. There's going to be a corner at B. There's going to be something else at C. We're just going to keep it generic right now. That will divide your graph up into pieces. Okay, so all the stuff that's happening up to A, and then what's happening between A and B, and then what's happening between B and C, and then what's happening over here. We call those intervals. So you're going to set up a table like we did before with those intervals. Then your job is going to be to choose a value from that interval. Everybody can choose different ones. It doesn't matter. That's the beauty of this, is that everybody can have independent idea. You're going to pick something that fits in that interval. So if, say, this was the x less than 3, I'm going to ask you to test that interval with any number that would be less than 3. And you could pick any number that you wanted. Your favorite number, a number you think is going to be easy. I love to pick 0s and 1s if I can. And then once we test those, then we will be setting up, okay, did it turn out to be positive or did it turn out to be negative? And then we'll test the next section. Does that turn out to be positive or negative again? Then, oh, maybe the next one's negative, and maybe then we're back to positive. So it's like what we did with velocity when we were checking, velocity and acceleration. Is it going to the right? Is it going to the left? Is it going up, down? That kind of thing. The pluses and the minuses are going to be helpful. What the pluses are going to tell us is if pluses mean the graph is going up. The minuses means the graph will be going down, because this is the value of what the slope is doing, what the derivative is. Positive derivative means the graph is going up. Negative derivative means the graph is going down. And we can do all of this without actually looking at the graph. You're not going to get to look at the original graph. So your next, let's see, we're on page 4, slide 4. Again, let the function be continuous. Let it have closed intervals. Then we use words like this. The function increases when the derivative is positive. So if I ever ask you why, don't tell me it is positive, tell me the derivative is positive. Or if I ask you, you say, the function will decrease because the derivative is negative. Use good words, use good language. The function will decrease, or the function is going down anytime that the derivative turns out to be negative. So those will be the minus sections of your interval. You will have a max anytime your table changes from a plus to a minus. Anytime you have a plus on the table changing to a minus on the table, you will have arrived at a maximum. Hopefully that will click with you, because the plus means the function is doing what? Going up. And then the minus means the function is now going down. So it has to have gotten to the highest peak it could possibly get, because it was going from up to down. So every plus to a minus, as the derivative changes, means you have found a maximum. On the flip side, every time you have a minus changing to a plus, that means you've found a minimum, because the minus means that the function had negative slope. It was going down, and then it was changing to going back up. So it can't go any further down, so you have reached its lowest point or its minimum. What if it's a plus plus? It means it was going up, and then it was going up again. Is that a maximum or a min? Neither. Okay, or a minus minus? Nothing. Only the change tells you the presence of a maximum or minimum. That gives you the x value. If you want to find the y value, you have to plug into the original curve. Some of you struggled with that on your test, so that you never went back to the original curve to find the full values of it. The chart will tell you the x values. If you want to know the y value, you're going to have to plug it back into the original curve to find the y value. We already talked about this. You're going to get things that are plus, minus, minus, plus, and you would need to know, okay, I see it's increasing, then decreasing some more, and then increasing again. So yeah, hang on, Jacob. So then you would say this minus changing to this minus here, going up, changing to going down. That means that A, that letter A, represents a max. So capital M, that's my A. So A is a max. What's B? Nothing. Okay, B is nothing, because a minus to a minus doesn't mean anything. It just means it was going down, and then it thought about it for a second, and then it decided to keep going down again. It paused and then went back down. But then changing from a minus to a plus means I am going down and then changing to going back up again. So that means my C value right there is going to be my lowercase m. That will be my minimum. Okay, Jacob.
I was just going to say, when we're thinking about the graph, we should think about like the original graph, not a derivative graph.
Right. We're picturing what the original, the derivative graph is describing for us what the original is. It's kind of like, I could look at a shadow of you, and I could figure out quite a bit about you from your shadow, but not quite everything. Okay, I might be able to figure out, like how tall you are from your shadow, kind of what your general body shape is from your shadow, but I wouldn't be able to tell what color hair you have or the shape of your, the color of your eyes from your shadow. But so from a derivative, we can tell a lot about a graph. Not everything, but there's a lot of key things we can tell.
On a derivative graph, can we find the maximum and minimum?
On a derivative graph, we can find the x values of it, but we wouldn't know what the y values were. Yeah, Rachel.
So the plus and minuses are from the derivative graph?
From the derivative, not from the derivative graph, from the derivative function, the values. Yeah, when we plug, we'll test something in that function. Okay? And so I could have a minus, minus, plus, plus. Maybe it would turn out like that. Okay, so what does that tell me A is? Nothing. What's B? A minimum. And what's C? Nothing. Okay, so the minus means the original graph is going down. And then the plus means the original graph is going up. And so that B right there is going to represent the minimum. So a minimum is happening at B. Those are samples. Let's try it with like a real thing. Let's do it for real. Without looking at a graph, so you have no access to a graph, find the local extreme values, that means maxes and mins, of the cubic. So I know that the local extreme values of a cubic have to happen. I know what a cubic looks like, right? I know that a cubic is going to go up and then down and then back up again. I know that that's going to happen. I know it doesn't have corners and I know it doesn't have cusps. But I do know that when it gets to its max, it will have a horizontal tangent. And when it gets to its min, it will have another horizontal tangent. But I don't have access to a graph. So I'm going to use calculus to help me. I'm going to find the derivative. The derivative will be 3x squared minus 27. And I'm going to set that derivative equal to 0 because I want to know when it's going to be horizontal. I can factor that. And I can factor it again. And because it's equal to 0, that tells me that that these things are happening at plus and minus 3. So I'm going to set up an interval that defines what's happening before negative 3. And then what's happening between negative 3 and positive 3. And what's happening after 3. Those are things I want to know. I don't need the last one. I just gave you extra. So pick a number less than negative 3. Anybody? Negative 5. In the derivative, plug in negative 5. Don't plug it in the original. It's not what I'm doing right now. I'm checking the derivative. So plug negative 5 into the derivative. I don't care what the exact number is. I just want to know if it's going to be a positive number or a negative number. That's all I care about. So in the derivative, I will take 3 times negative 5. I'll square it and I'll minus 27. What kind of number will that turn out to be? That'll be positive for sure. I don't need to know exactly what the number is. I just need to know it would be positive. All right, what if Nathan had picked a different number other than, what if he'd picked negative 4? Still be positive. What if he'd pick negative 100? Still be positive. Every number you pick that's less than negative 3 would result in a positive number, which means the graph is going up. And does my graph go up? It sure did. All right, pick me a number between negative 3 and 3. Sure, 0 is great. So we'll test 0. So 0 squared minus 27. What will that turn out to be? Negative. So I just changed from positive values to negative values. When I change from positive to negative, that means the graph changed from going up to going down, which means what's happening at negative 3? negative 3 is the max. So I can assume x equals negative 3 is max. Then we'll pick a number greater than 3. One of the numbers I like to test, if I can't test 0 or 1, I always like 10, because things going by tens are always easy to work with for math. So 3 times 10 squared minus 27. That's back to positive again, which means my graph is back to going up, and it does. And because I'm changing from negative to positive, that means that x equals positive 3 is a min. Now,
A min or a min?
it is not the min. That's a good question. Because are there values that are lower than that?
Yeah.
Yeah, that arrow on the left side goes down farther and farther. So it's not the absolute min. It's a relative min for this section, but it's not the absolute. It's not the lowest of the low. There are still lower values. But it is what's called an extreme value locally in that section. Yeah,
So if this was like a question on the quiz, you could just say it's the min,
it's a min.
a min, okay,
A is better than the unless you're asked to find the absolute.
and it's like a min,
Like a parabola has an absolute min
okay. Yeah,
because both ends of the parabola go up and nothing will ever be lower than that,
yeah.
right? But we know that there will be things that are lower than this minimum and there will be ones that are higher than the maximum. Okay, yeah, Isaiah.
For a function like sine, can you say that either 1 or negative 1 is the absolute max or min? Despite
Yeah,
the fact
so
that it can
some of these you're going to just know because you know what the shape of the graph is, but probably not going to give you just sine. Probably going to give you some other function, sine of something.
Are
But
you able to say that it is, despite the fact that it continues forever?
okay, yes, and so you would maybe do that as a more of a pattern. Like you would say the minimums are going to happen every k pi over 2. Okay, so every time we hit k pi over 2, we're going to hit that cycle. Okay. All right, let's try another one. Now this is a little tougher. This is a kintic. Okay, this is a degree 5. So I do know a little bit about degree 5s. I know that degree 5s look like this, and then they finally end up going up, or kind of maybe they sort of do that. I know that, but I don't know exactly where the maxes and the mins are, but I can use what I do know about calculus, that it doesn't have any corners, but it's going to have 4 horizontal tangents for me to find. So f prime. Let's find those horizontal tangents. So 5x to the 4th minus 20x to the 3rd plus 15x squared. You're going to have to catch me and see if I make any of these mistakes. This whole daylight savings time I'm still a little off. So if you see a mistake, to find the horizontal tangents, I will be setting this equal to 0. When I notice that you're not setting things equal to 0, that would be something I would deduct points for. You can't factor if it's not set equal to 0. It has to be set equal to 0 to show that you're understanding you're finding horizontal tangents. All right, what can I factor out of this?
5x squared.
Great, let's take a 5x squared out. That will leave me with x squared minus 4x plus 3. That can be factored again. That can factor into x minus 3 and x minus 1. That's going to give me some solutions. It's going to give me 1, 3, and 0. So then I'm going to set up my chart. I'm going to have x less than, the lowest one was 0. Then between 0 and 1. And then between 1 and 3. And then greater than 3. I thought maybe I was going to have 4 horizontal tangents. Turns out I don't. Turns out I only have 3 horizontal tangents. So my thought about this kintic was not quite right. Probably is going to be more like this. It's a pause, and then it goes back down again. Something like that. Now I only have 3 horizontal tangents. So it could be something more like that. All right, so we're just going to pick our numbers and we're going to test them in our derivatives. I find math is easier if you test it in the factored form instead of testing it back in the full-on foiled out form. I'd rather plug it into the factored form personally. Okay, so let me show you why. Pick me a number less than 0. Okay, so I'm going to test it in this version. I feel like I can do math better on that. I can do 5 times -1 squared times, okay, if I put -1 into x minus 3, what will I get? I'm going to just positive or negative. I'm going to get a negative sign. And if I put -1 into the last factor, what am I going to get? A negative sign. So I just like to count up how many negatives I have. I don't care what the actual number is. I just know I'm going to have a 5. I'm going to have a -1 squared. What's going to happen to that? That's going to be positive. So I've got positive 5, another positive, and then 2 negatives. So altogether, what do I have? Positive. I feel like for me, it's easier for me to count positive and negatives than it is to go back to the beginning and be thinking about 5, adding 20, subtracting 15, working out like that. Okay, pick me a number between 0 and 1, probably a half. All right, so I'm going to have 5, and then I'm going to have a half squared, and then in x minus 3, if I plug half there, what am I going to get? A negative number. And then if I plug half in the next one, I'm going to get a negative number. So I'm going to have a 5, which is positive, a half, which is positive, and then 2 negatives. So what does that tell me? Still a positive. So what does that tell me about 0? 0 is nothing. Okay, 0 is where nothing special is happening. It was going up, it paused, it thought about it a minute, and then it decided to continue going back up again. All right, pick me a number between 1 and 3. 2. Okay, so we'll go do 5 times 2 squared. All right, what about 2 minus 3? That'll be a negative number. What about 2 minus 1? Positive number. So now for the first time, I have a 5, which is positive, a 4, which is positive. I only have 1 negative sign, so this is going to be negative. What does that tell me about 1? Okay, the number 1 is because I'm changing from a plus to a minus. That means my function is increasing, changing to decreasing. So I have my first chance right here. X equals 1 is a max because of the way the change happened. And then finally, I'll pick something greater than 3. I like to pick 10 when I can. So I'll have 5 times 10 squared. And then 10 minus 3 is a positive number, and 10 minus 1 is a positive number. So overall, that will be positive, which tells me that x equals 3 is a min. So I could go back and I could adjust my Kintic even further. It's really not going to look like that either. My best bet is that this function is going up. Let me do it in black. The function is going up. It pauses and then continues to go up some more. It will reach a max. It will come back down. It will reach a min. And then it will finally go back up again. That could be a possibility. And here are there's a horizontal tangent here, here, and here. 0, 1, and 3. That would be a sample. Yeah.
If that's fun x, then you would plug that into the original graph to find the y.
If I wanted to know the actual coordinates,
Because that's fun the absolute, would you have to plug that in back to the original function?
yeah, so if I wanted to know if x equals 1 is a max, what is its y coordinate? I'd have to go back up to the original and plug 1 into the max, and it turns out to be 21, so I know that the coordinates are 121. But it still can't be an absolute because the ends of that Kintic are still going past higher than 21. So this might be at 21, but the rest of the graph, so it's still only a relative.
I know
It's,
what I'm trying to ask is like if there was like multiple maxes and
Mhm.
bins, find like the guess the highest or
you'd have to compare them.
compare them, you'd have to find the y.
That's exactly right. All right, any other questions on that before we keep going? Okay. All right, they do, gives our last one. All right, we don't know very much about this drawing at all. X times the square, I know what the square root of x squared minus 4 looks like by itself, but I don't know what x times the square root of x squared minus 4 looks like by itself, so I really have no idea what is going on here. I do know, however, that this does not go on forever. This has endpoints, because what can a square root never be? Okay, a square root can never be negative. And so I do have endpoints here, and I have endpoints that are -2 and +2. I can't go anything outside of either of those. If I try to plug in anything that's going to be, like if I tried to plug in 0, I'd have a problem because I'd have a negative number. Tried to plug in 1, I'm going to have a problem. So I do have endpoints. In fact, I have to make sure everything is either less than -2, and I have to make sure everything is greater than +2 in order to keep things straight. But let's figure out where there might be horizontal tangents and there might be corners and cusps. So f prime of x. What am I going to need for this derivative? Not even just chain rule. I'm also going to need product rule. So my product rule starts with, this is why we don't have to review for the exam because we just keep using everything we used before. The product rule starts with x squared minus 4 under the rad times 1 plus x times, and now I need the rad here, which is half times x squared minus 4 to the -½ times the chain rule of 2x. So you won't get rusty on your product rule, trust me. We're going to keep using product and chain. So this becomes square root x squared minus 4. And then the other one has a numerator and a denominator. What's in the numerator?
2x squared.
But doesn't the 2 here reduce with the half here? So the numerator is just x squared. And what's in the denominator? There we have our rad, x squared minus 4. Before you set that equal to 0, you don't want to jump right to that. You need to get a common denominator. So this is going to be some math. What is the existing denominator right now under the original x squared minus 4? 1. So what do I need to multiply it by? Another x squared minus 4. I need to multiply the top by x squared minus 4. This is going to give me a common denominator. The common denominator is rad x squared minus 4. The numerator becomes x squared minus 4 plus x squared. That's rad x squared minus 4 times another rad x squared minus 4. That makes regular x squared minus 4 plus x squared. So if you don't mind, I'm just going to put that all together and say that that is 2x squared minus 4. Now I want to find if this graph has any horizontal tangents, or what else might this graph have? Might have corners and cusps. So if I'm going to find horizontal tangents, then I take this derivative and I cross multiply it with 0 over 1. That'll find me any horizontal tangents. If I want to find corners or cusps, I take the same derivative and I cross multiply it with 1 over 0. That's going to find me if it has any corners or cusps. The only reason I didn't do this last time is because I knew that a cubic didn't have corners and cusps, and I knew that a polynomial didn't have corners and cusps, but this one sure might. When we do the math and we cross multiply, I'm not going to do all the little steps with you. I'm just going to show you what we solve. we get that there are horizontal tangents at plus or minus rad 2. And we get that there are corners and cusps when we cross multiply and we solve. We will get corners and cusps at plus or minus regular 2. Okay, any questions so far? So what should I do with those numbers? Make a chart. Okay, so what's the smallest of those numbers? Negative 2 is the smallest. So I'll have x less than negative 2. What's the next smallest? Negative rad 2. So I will have negative 2 up to negative rad 2. The next would be positive rad 2. So I'm going to have negative rad 2 up to positive rad 2. Then positive rad 2 up to 2, which is the biggest, and I need another one. I needed to add an extra, x greater than 2. So you want to pick numbers that are within those intervals and test them in the derivative. Don't test them in the original problem, test them in the derivative. So I'm going to pick a number less than negative 2. I'm going to pick something crazy like negative 10. And in the derivative, I'm going to test it. 2 times negative 10 squared minus 4 over the denominator of the rad of 10 squared minus 4. Do I really care what that turns out to be? What do I mostly care about? Okay, what's the numerator going to be? Positive. What's the denominator going to be? Positive. So this whole thing is positive, which means the graph is going in what direction? Up. Then we pick another number, okay, in the next section, okay, that might work. So negative 1 is not between negative 2 and negative rad 2, because negative rad 2 is 1.414. So you'd have to pick like 1.5, okay? So 2 times 1.5 squared minus 4 over 1.5 squared minus 4. What do I get in the numerator? A negative number. What do I get in the denominator? Careful. What do you get in the denominator? It doesn't exist. All right. What would be the obvious one to pick in the next interval? 0. Okay. 2 times 0 squared minus 4, that's negative. But 0 squared minus 4, that doesn't exist either. Neither does the next one. No, not necessarily. The last one does turn out to be positive, which means the graph is going up again. So do I have any maxes or mins? Nope. Didn't have any.